Okay, so let's talk a little bit about valence bond theory. So, in the past, we talked about VSEPR models, and we talked about how that allows us to get a good idea of what molecules look like three-dimensionally. Well, now we're going to step it up a notch, and we're going to look at valence bond theory, which is going to allow us to show how covalent bonds actually form between atoms within a molecule. And we're going to show this through a process called hybridization. So when you hear the term valence bond theory, what I want you to associate that with is hybridization. The reason it's called a hybridization is because you're going to take your central atom in your molecule and you're going to show how it takes on a hybrid form, which basically means it's going to fuse together some of its orbitals in order to make enough slots available to make the covalent bonds that are in the molecule itself. And ultimately, those hybrid structures for those central atoms are going to be based on the number of electron domains that are around that central atom. And we saw that to a certain extent with the VSEPR model, where you counted the number of domains around your atom and that determined your molecular geometry. Well, here we're going to count the number of electron domains in order to figure out what our hybrid form is going to be for a molecule. So when you have two electron domains around your central atom, that's going to give you an sp hybridized structure. And the reason it gives you an sp hybridized structure is because for a covalent bond with two domains, you're going to take the s orbital, which remember the s is just that one line, and you're going to fuse it to one of the p orbitals. Remember that for your p orbital you have three lines, so this represents three different orbitals. So you'll fuse the s with one of the p's, and that's going to give you the sp hybridized orbital, which gives you two convenient slots for making two bonds or two domains with that hybridized form. When you have three electron domains, that's when you're going to see the sp2 hybridized form take place. So again, we're going to take the s and we're going to fuse it to two of the p orbitals. So we're going to fuse these together, and we got the one line here, two lines here, so add those up. That's going to give you a total of three slots in what is now called the sp2 hybridized orbital. And just to make this clear, the reason it's called sp2 is because one of the lines comes from the s right here, and these two lines come from the p. So one s and two p's makes it sp2. This gives us three slots now for making bonds. When you have four electron domains, what you're going to do is fuse the s with all three of the p orbitals. And that's going to give you four slots for bonding. And this is going to be called sp3. And I will tell you right now, sp3 is a pretty common one. And sp3 is the same thing as tetrahedral to a certain extent. For molecular, for electron geometry at least, sp3 is going to be coordinated with tetrahedral as an electron geometry, because of those four different bonds that you can make with an sp3 hybridized structure. And it's one that you see quite often. So now let's talk about some special cases down here. So ultimately, down here we're only going to see 5 and 6 domains, when we have expanded octets. And remember, you can only have expanded octets when you get to the third row and beyond on the periodic table. Well, why is that? You can actually explain expanded octets using hybridized methods. So we know that the D block starts at row 3. You don't have a 2D, you start with 3D. So that means that for the 2P row, there is no D block right after it. So once you hit 2P, you automatically go to 3S. There's no D block in between. But when you get to 3P and beyond, all of a sudden you have a D block in between now where you can store extra electrons. You can make extended hybridized structures. So when you have 5 domains, what you're going to do is fuse the S, all 3 P's, and one of the D orbitals. Remember that you have a total of 5 D orbitals. Just take one of those D's, fuse it with the 3 P's, fuse it with the S, and that will give you the sp3d hybridized form. Same thing is true when you have 6 domains. That's going to give you sp3d2, which means you tack on an additional d orbital. So now you've got 2 d orbitals fused to the 3p orbitals, fused to the 1s orbital, and that's going to give you 6 open slots for bonding. But we can only do these 2 for expanded octets. These 3 up here, where you have 2, 3, and 4 domains, are probably the most common ones that you'll see, and you'll see them all the time with carbon. Because we often will start thinking about carbon in terms of how it's hybridized within a molecule. And that's a very important tenet of organic chemistry, where you almost always have to think about how the carbon is hybridized within every molecule you'll look at. So now that we've actually gone over what happens with hybridized formation, now let's actually look at it in the context of an actual molecule. So here I've got the carbon dioxide molecule, CO2. So what I want you to do, go ahead, pause the video, and see if you can draw the valid Lewis structure for CO2, because you have to be on top of your Lewis structures. If not, everything else is going to fall. Your geometry is going to be wrong, and your hybridized forms are going to be wrong if you cannot draw the correct Lewis structure. So make sure you get on this if you can. So go ahead and see if you can draw this CO2 molecule for its valid Lewis structure. Hopefully you drew something like this, because this is the correct Lewis structure for CO2. So we know that carbon is going to be our central atom here, and what we want to do to figure out the hybrid form is count the number of domains around the carbon. Well, this is a domain here, this is a domain here, therefore we have 2 domains around this carbon, and when we have 2 domains, if you remember, that's going to give us an sp hybridized form, because sp is what correlates to 2 domains. So that's going to give us an sp form. Now I also want to talk a little bit about types of bonds. So in the valence bond theory, there's 2 types of bonds that you can have. A sigma bond and a pi bond. A single bond is going to be equal to 1 sigma bond. So if you see a single bond in your structure, that's equal to 1 sigma bond. And a sigma bond is where you're going to have an overlap between a hybridized orbital and another orbital. So sigma bonds always represent an overlap with a hybridized orbital. A double bond is going to include that sigma bond with something additional called a pi bond. So with a double bond, we're still going to have a sigma bond there, but we're also going to have the addition of the pi bond. And a pi bond is going to be an overlap between unhybridized p orbitals. So for some structures, you're going to have p orbitals that aren't included in the hybridization that takes place. And ultimately, when you have electrons that are shared in that unhybridized p block, or p orbital, I should say, that's going to give you what's called a pi bond. And for a double bond, we have one sigma bond and one pi bond. For a triple bond, we have one sigma bond and two pi bonds. And again, like I said, the orbitals in the valence bond theory are going to overlap. So for our CO2 molecule, let's see, we have two double bonds here. So we have a double bond going to this oxygen, and we have a double bond going to this oxygen. So that means that this bond here has one sigma bond, which we write as this. This is the Greek letter sigma, the lowercase sigma. So this would have one sigma bond, but it would also have one pi bond. And the same thing is true for this double bond over here. In this double bond, we have one sigma bond, and we have one pi bond, because we have a double bond there. But let's actually get into the nitty-gritty of how this sp hybridized structure forms for the CO2 molecule. Let's actually break it down in terms of where the electrons are actually moving to create this hybridized form. So what I've done here is I've taken each of our components of the CO2 molecule, one carbon and two oxygens, and I've drawn some orbital diagrams to show the electrons that we'll be using to make the overlaps here to make the covalent bonds. So this oxygen here, I've tried to color code these last two electrons in red. We'll be seeing why that is in a second. And for this oxygen over here, I've color coded those last two electrons in green. But for the carbon, what we need to do is we need to actually make the hybrid orbital. So like I said before, we're going to fuse some of these orbitals together to make the hybrid form. And we know for CO2, it's going to take the sp form. So to take the sp form, what we're going to do is we're going to fuse this s orbital with one of these p orbitals. And that's going to give us the sp, and it's also going to leave us two unhybridized p orbitals up here. That's where our pi bonds are going to be made. So our pi bonds are going to be made up here in the unhybridized, the ones that we didn't include, and the sigma bonds are going to be made from this hybridized form here with the sp hybrid structure. And ultimately what you want to do is see this downspun electron here that's sticking down. You're going to want to move this up here into this empty slot. And the reason that is because when we make our hybrid structures, we want our electrons to be evenly spread throughout all the slots, because that's going to help us when we go to make our bonds. So just note to yourself that when you make these hybrid structures, you want to spread those electrons out evenly in your central atom. So just take that downspun electron here and move it to that empty slot. That's going to matter when we go to make our hybrid structure. Okay, now I've shown that hybrid structure formed, so now we have our sp orbital with these two empty or half-empty slots, and we have the unhybridized 2p still up here with their open unhybridized slots ready to go. So essentially now the carbon is ready to start bonding with these two oxygens. So what I'm going to do with the oxygens is I'm going to take them one at a time and show you where each electron is going in terms of the structure. So let's start with this electron here. Apologize for my clock going off. So what we're going to do with this electron here is I'm going to move it to this empty slot right here. And it's going to become a downspun electron right here. So we're taking this electron here and moving it to this empty slot right here. And that's going to create the sigma bond between the carbon and this oxygen. So this is one of our sigma bonds for this molecule. Conversely, for this oxygen here, I'm going to take this electron right here, and I'm going to move it to this empty slot right here. and it's going to become a downspun electron in this hybrid orbital. So we're taking this electron and removing it to this slot right here. And this is going to form the other sigma bond between those two, between the carbon and the oxygen. So what about the other two electrons? Well, this electron for oxygen right here is going to come up to this unhybridized P up here, and it's going to form a pi bond. Because remember, we said that pi bonds are formed between unhybridized orbitals. So we know these two slots up here are not in the hybridized form. So that overlap between these two electrons, because this red electron here is going to become a downspun electron here, that's going to form a pi bond. Same thing for the other green electron for this other oxygen. It's going to come right here to this slot right there, and it's going to form the other pi bond for this molecule. So we see how this electron and this electron form the sigma bond because those electrons are going into the hybrid orbital. Electrons that go in the hybrid orbital are your sigma bonds. Electrons that go into your unhybridized p orbitals, they are the pi bonds. They are the electrons that make up the pi bonds in your molecule. So now we've shown the electrons actually moving around. What would this structure actually look like then if we were to draw it three-dimensionally using these hybridized and pi bond notations? So this is what that CO2 molecule would look like in terms of its hybridized orbital overlap. And you're probably thinking to yourself, what in the world is this? And I admit, it's a little weird. And they will look a little weird. But you've got to free your mind in terms of how you think about atoms and molecules and what they look like. Because they do look really weird. So basically what's going on here is we've got our carbon in the middle. And these orange guys coming off are the sp orbitals. So right here, this sp hybridized structure, that's what these two orange pillars coming off of the C are. And the red guys here coming off of each oxygen are the p orbitals of the oxygen. So each of these oxygens has a p orbital, and these p orbitals are what's shown here. And the sigma bond is the overlap right here and right here between the hybridized orbital of the carbon and the p orbital of the oxygens. That's what makes your sigma bonds. So each of these would be our sigma bonds. And then these blue guys that look a little weird, look like little hooks going to the oxygens and the carbon, these are going to be our pi bonds. And that's where we have those unhybridized orbitals being overlapped. So hopefully it doesn't look a little too weird. Just keep the shapes in mind. S orbitals are a circle. So if you want to draw S orbitals, they're like a little circle. P orbitals are kind of like long balloons. Hybridized orbitals are kind of fat balloons like this. And pi bonds look like these little hooks going from each of the elements. And both of these represent one pi bond. So one pi bond is represented by two hooks going, one is on top, one is on the bottom. So together this makes two pi bonds. One pi bond is going to this oxygen, one pi bond is going to this oxygen. So that's sort of the basics behind hybridization and hybrid structures. The name of the game here is that you want to count your electron domains from your Lewis structure, use that to determine your hybrid structure, your hybrid form. In some cases, that's all you'll need to do. In a few circumstances, you might need to show the overlap, or you might actually have to draw what the molecule looks like based on the bond overlaps. And that's kind of how you would do it. You would draw your hybrid orbital, draw your regular orbital, show them overlapping like a Venn diagram. And for your pi bonds, if you have any pi bonds, in some cases you won't have any pi bonds, but if you do happen to have pi bonds, you want to draw them like hooks going between each element. So that is sort of the name of the game when it comes to valence bond theory.